In mathematics and physics, a very famous problem was what's known as the n-body problem. An n-body problem is a problem where you have n bodies, where n can be any natural number, say 1, 2, 3, 4, or 40 if you're feeling really crazy, bodies, in which the only forces acting upon the bodies are emanating from the bodies themselves. Today we're going to look at a two-body system in which we have two planets gravitationally attracted to each other. Now one might say, well, one planet is just going to orbit the other. Well, that's not entirely true. What happens is that they both orbit their collective center of mass. But we can take this two-body problem and reduce it down to a one-body problem using what's called a reduced mass.
So how do we find this reduced mass? Well, let's not think so much so about the mass right now and think more about how this mass moves. In particular, we want its radial acceleration. So how do we find that? Well, let's consider the distance of this reduced mass. What is that distance? Well, put simply, it'll be the sum of the distances of the second mass and the first mass taken as vectors from the center of mass, just summated together, like so. And position of mass 2 minus the position of mass 1. To find the acceleration, we differentiate this 2 times with respect to time, and we find that the acceleration of our reduced mass is just the acceleration of our second mass minus the acceleration of our first mass. We can now go about deriving the reduced mass, but first let's take a little look at the forces. So we know that m1 and m2 both exert forces on each other, but how do we characterize those forces? Well, it's pretty simple. Using Newton's second law, we can find that the force m1 exerts on m2 is just m2 times its acceleration, a2, and then the same thing for m1. All forces have equal and opposite reactions, meaning that these forces will be equal, but we'll have to put a negative sign on one of them because they're going opposite directions. Substituting the right-hand sides of these equations in, we obtain this, and isolating for a1, we get this. Substituting in the equation we found earlier, after some algebraic manipulation, we can arrive at equation 2. Now what we're going to do is we're going to take equation 2 and we're going to multiply both sides by m2. So we get m2 times a, which doesn't give us anything because we haven't defined it, but m2a2 we have defined. It's f12. We're going to divide both sides, and on the left side, the product of the masses over the sum of the masses, which is what we defined as the reduced mass, times the reduced acceleration, and it gives us f12. So what have we proven here? Well, we've shown that if we take this reduced mass, multiply it by a reduced acceleration, we still get the unreduced force. The reduced system is mathematically the same as the unreduced system.
So why is this reduced mass important? Well, for one, the reduced mass is required in order to mathematically prove Kepler's second law of planetary motion. As well, quantum physicists use the concept of the reduced mass to help characterize the way in which electrons orbit around atom nuclei. Thank you for watching. My name is Jason Yee, and E is still irrational.